So with this mission, our primary goal is to establish permanent bases on Mars. But on the way, we're going to use the Moon and Phobos as stepping stones. We're going to be starting off with some international moon bases, and then from there we can move to putting a smaller base on Phobos, operating robotically some cranes and rovers on the surface, and then actually once we get to about 2040, fully establishing and manning a base on Mars. The moon bases are intended to test all the technologies that we need for the later missions that we're going to do. At the same time, we'll also be doing some testing on the Earth and Hawaii and other places to make sure that all of our modules are ready for the Martian surface and in space.
We will have 3 bases at the moon, one at the far side, one at the near side, and the most interesting of them all, look at the South Pole at Shackleton Crater.
Each lunar base will be composed of 3 second-generation exploration modules.
It is at Shackleton Crater where we will produce rocket fuel from the water extracted from the icy regolith from the moon. We want to produce rocket fuel from the moon because bringing all the rocket fuel to go to Mars from Earth is extremely expensive due to our Earth's high gravity and atmosphere.
The Cycler is a manned spacecraft designed for delivering astronauts to Mars and Phobos safely and efficiently. Analogous to a shuttle bus on Earth, it will be orbiting the Sun and meeting Earth and Mars at regular intervals throughout the mission.
The Cycler vehicle will orbit in an S1L1 trajectory. This trajectory allows for a large vehicle to remain in orbit and for smaller taxi-like vehicles, known as the human landers, to bring humans to and from the Cycler. The S1L1 trajectory is a heliocentric orbit that uses gravity assists at both Earth and Mars to minimize the number of propulsive maneuvers necessary. This solution allows for a larger living space for the humans on their journey from Earth to Mars. Because the orbit opportunity exists each synodic period, but this is a 2-synodic period cycler, we will use 2 cycler vehicles to maximize the number of trips from Earth to Mars. An important consideration for long-duration, low-gravity human spaceflight is the time of flight for the crew. The S1L1 has a time of flight from Earth to Mars of only 138 to 183 days. This short duration allows for the crew's mental and physical health to be maintained. Cycler vehicles will also serve as communications satellites. Once both cycler vehicles are in orbit, we will be able to maintain continuous coverage, even when Earth and Mars are in solar conjunction.
To begin, a boost vehicle will be launched to low Earth orbit. After this, 3 human landers will be launched and docked separately with a boost vehicle. Then, this 4-vehicle assembly will be boosted out of Earth's orbit to meet with a cycler using a hyperbolic rendezvous.
To get the crew from low Earth orbit to the cycler, we will need to perform a hyperbolic rendezvous. This is dangerous. If anything goes wrong, we could lose the crew. Because the hyperbolic rendezvous has never been done before, we will perform 2 tests using cargo to ensure everything goes as planned once the astronauts are ready to make their journey. The first cycler vehicle, Cycler A, will carry 6 astronauts to Phobos. These astronauts will be in charge of surface operations on Mars while we construct the colony. The second cycler vehicle, Cycler B, will come 1 synodic period later, and it will carry 18 astronauts. 6 of these will go to replace the crew on Phobos. The other 12 will go to the surface of Mars and join the crew of 6 from Phobos. These will be the first men and women to ever step foot on another planet. From there, 18 astronauts will continue to come on each cycle.
In order to meet the 280 kilowatt power demand, we will employ 2 ATK solar panels.
Around Mars, the solar flux available is only 40% of the solar flux available around the Earth. These solar panels are circular and flexible. This design allows them to be very lightweight and to have a very few storage volume.
These flexible wings are 28 meters in diameter and are capable of folding up like a Japanese fan in order to fit inside a small fairing for launch.
The first floor of the XM3 it houses the power systems, thermal systems, water systems, and life support systems, all necessary for crew survival. The second floor contains like a lab space and a group habitat space. On the third floor is the habitat's personal space.
The human lander, or hula, is what's going to be the capsule that contains the first 6 crew members on every mission.
Inside the human lander, there'll be 2 rows of 3 seats each. The astronauts leave the cycler and land on either Phobos or Mars. Either of these journeys will take approximately 1.3 days.
Upon leaving the cycler, the human lander will approach Mars in a hyperbolic trajectory, such as this, where we will be performing an aerocapture maneuver where we skim the atmosphere and then head out either to Phobos or back around for a direct entry at Mars. To enter Mars, we have a heat shield which is mechanically deployable. We'll be deploying this in space upon leaving the cycler, and this will take the brunt of the heat force and the deceleration maneuvers. Upon descent, this will decelerate us to a reasonable speed, and then we will deploy a volute in order to decrease the speed even further. The high heating will be absorbed by the heat shield, and the volute will do a lot of the deceleration in the final descent stage. Upon reaching a reasonable terminal velocity, a propulsion system will be ignited, the heat shield will be dropped, and the balloon will be cut. The terminal propulsion system will bring us down to a 0 vertical velocity and cause a hover maneuver where we can move laterally if need be to increase the accuracy of landing. We will deploy landing gear and finally land directly on the Martian surface.
On the Martian surface, the human lander will transform into a rover. The crane will pick up the human lander and place it onto a chassis. The human lander will then be able to travel up to 20 kilometers per hour and go up an incline of approximately 30 degrees.
The main value of the Phobos base is that we're being able to eliminate the 24-minute time delay that can happen between Earth and Mars.
The Phobos base will be composed of 3 XM3s and 2 human landers. This will be the home to the crew of 6.
Back on the surface of Mars, the main colony is made up of 9 connected XM3 modules. 3 in the center as the crew living quarters, 2 additional on the outside to serve as water processing storage, 2 other out here to serve as farming, and then 1 extra core module and another module to serve as the medical bay. Together, these modules form the entirety of the colony and will house at most a 54-person crew.
Even if it were possible for the colonists on Mars and Phobos to be able to produce 100% of their food, water, oxygen, and nitrogen, there are just some things that cannot be produced on these bodies. That's where the cargo lander, or Carla, comes in. Carla is the primary source for all resupply needs for the colonists on Mars and Phobos. The cargo vehicle will be using Hohmann transfers to get from low Earth orbit to the orbit at Mars. Once it arrives at Mars, it will then detach and leave the rest of the vehicle to enter into the Martian atmosphere. Upon landing, it's up for the colonists to locate and retrieve the Carla capsule and bring it back to the main base.
The Mars Return Option, or MARIO, is a series of missions that is designed to bring a crew of up to 6 back to Earth from Phobos or Mars. That is where the Mars Ascent Module, or the MAM, comes in. The MAM will be on top of its own rocket that will then bring the vehicle up to Phobos. From here, the crew of the MAM will dock with the human lander on Phobos and continue the journey back with the BA-330 and the Phobos return system with up to 3 of the crew from Phobos to give us our crew of 6.